Okay, we're coming up on near the end of the lab, and the next part that we're going to do is a big design. So let's make a new cell, and we'll call it my big design. And let's make the schematic first. And you guys should make the exact same schematic that I'm going to make, so that when I'm marking your assignments, everything is the same. So I'm going to put in some AND gates. And an XOR gate. Couple of inverters. And a NOR gate. And an AND gate. Okay, now let's wire all of these guys together. Almost done. So far so good. Let's add some pins on there. Create pin. I'm going to do them all at once, or at least all the inputs first. So let's have A, B, C, D, and we'll make them inputs. A, B, C, D, and we need one more as an output. Let's just call that guy out. So that's our schematic. We'll check and save that. And now we're done with the schematic. Now what I want you to do is create a layout for that schematic, and you can use any technique you want, really. I'm going to go through one way, but you could do all of this entirely by hand if you wanted to. If you want to know what size transistors to use, of course, you just drill down. So if I double click on, for example, this gate, look inside of it, there are my transistors. I'm going to be a bit lazy though. I'm going to launch layout GXL and tell it to create a new layout automatically. So this should be of type layout. My Big Design is the correct name. Click OK. Now my layout window is open. Make this a bit bigger. I can see what's going on here. And now there's a variety of ways you can use this tool. So I'm going to go through one way as quickly as I can, and then you guys should definitely experiment with this and try generating different types of layouts. Let's see. I guess I could do it very quickly from here. Generate all from source. Now, there's a bunch of stuff here. I couldn't get the chaining to work. Maybe one of you guys can figure that out. I wanted to make a row of standard cells and have them automatically chained together. You should be able to do that, although when I look in the documentation it seems to be more geared towards individual MOSFETs. But something tells me devices should work too. I didn't spend a lot of time on it, but you guys have all the time, so why not? Anyway, we're going to generate all the instances in our schematic, all the I/O pins, and a place and route boundary. Everything else looks good. We'll get it to automatically extract connectivity after the generation. For the I/O pins, let's make them big enough so we can see them. So maybe maybe a micron by a micron. We'll put them on the metal one layer, pin layer. And let's apply that, and then pin labels. Let's create the labels as a text display. So we'll make the height 0.2, font stick. Layer name, let's use the text layer. Everything else is okay. Now let's go to the next tab, the PR boundary. PR boundary. So we'll get it to estimate what size of chip to make for us. Let's just change this. So we'll get something that's, let's say, 3 times as wide as it is tall. And under floor plan, this should all be fine. Okay, click OK. There we go. Now, oops. This is our place and route boundary, so when we try to do the routing and placing later, it's going to try to fit all of this stuff within this area. I could have made that smaller, but just so we can see what's happening, that's okay. I've got nets turned on right here. I just press the E key. I can turn them off, and all those white lines go away. These are our pins. So we had, let's count them up here, we had 4 inputs, 1 output, so that's 5 pins, and then there's also a power and a ground pin. So that's where we get 7 pins total. Now let's see, I think I remember you can automatically get it to place the pins for you first. Let's see how to do that. I think that was, maybe it was Pin Optimizer. Pin placement, and I'm going to put the power at the top edge. I'll put the ground at the bottom edge. I'll put the inputs on the left hand side, and I'll put the output on the right hand side. Don't have to do this, but I'm doing it. Oh, I forgot to hit apply. That's horrible. Let's do this quickly again. There we go. That's what I wanted. Everything else should be okay. So I can close that. And you can see now how they're placed. So they're put up there. Now, I'm going to try to get Cadence to automatically put the rest of this stuff in this box. See if it can fit it in there for us. I don't know if it can fit. We'll see. Okay, so I need to go next to place, and I'm going to place some custom digital logic here. Let's plan for the placement. Place everything within the boundary. There's different types of styles of layouts you can choose. We're going to do an assisted standard cell type layout. The region where we're going to place it, I can specify that. I'm going to leave that blank. I think it should automatically just go for the place and root boundary. We'll see. Rows, try to get horizontal rows, but this is what I said before. It doesn't seem to be working. At least I'm not smart enough to figure out how to get it to work. And the rails, for power and ground rails, let's choose metal 9 and metal 8. Let's see if it does anything. Layout generation will regenerate everything. Close that. Go back to custom digital placer now. Okay, check to make sure you have the checkbox is the same as me. This should be fine. Everything else there looks good. This is kind of neat if you check on this checkbox here, show placement progress. You'll get to see what Cadence is thinking about as it does the optimization. Now I'm going to click apply, and you can see it's moving those standard cells around inside of that box, and for whatever reason it chose this as an optimum placement. I think a person could probably do better. Let's zoom in on that and see what's up. So you can see it's actually not got everything in a straight line. Obviously it's chosen some crazy placement that it thinks is optimal based on the information we've given it so far. So the next step would be to do the actual routing. So I can go up here to route. I could just choose automatic routing. That's a quick one. Let's try that. It'll use up to metal 9. We could choose a lower metal if we wanted to. We'll make it route the whole cell view. It's going to route nets. Oh, this form is too long for this the size of my screen, so I think I can get this to, yeah, I can move that around using Alt and then pressing the left button. So let's run that. So it is running, and I remember there is a screen where you can monitor what's going on. It's not that one, that's the placer. Maybe it's the main window. Yeah, so you can monitor what's happening. It takes a little while, even on this fast workstation. It's pretty slow, but it's finished. Okay, so that would be the final routed chip, including all inputs, outputs, power and ground, and connections between all of the standard cells. Now obviously this is not a standard cell type layout, and obviously it's not area optimized. So as part of your assignment, you're going to figure out how to get a standard cell type layout using this tool. The other thing I'm going to ask you to do in the assignment is to do an LVS for this layout versus the schematic. Now in order to do that, first you'll do an extraction, just like we did for the inverter, and then you'll use the extracted view and the schematic view in the LVS program to do the layout versus schematic comparison.